Okay, so welcome everyone. Today we're going to go through some of the nuts and bolts of symmetry breaking in quantum and classical field theory. This phenomenon is ubiquitous. It's one of the first interesting non-perturbative statements that you learn in quantum field theory. And making effective use of this allows you to explain phenomena from high energy physics to condensed matter physics and so on. It's like, from superfluids and superconductors to the Higgs mechanism, although it's a slightly different, as we'll discuss, but still the ideas relating to spontaneous symmetry breaking are at the heart of all of them. So I thought that we would start with the quantum case, actually, that we would start by discussing the implications of having spontaneously broken symmetry, which means that the vacuum of some quantum field theory is not invariant under the action of the charge operator. And we'll try and see how that statement leads to the conclusion that there must be a massless particle in the spectrum of the theory. So this connection between spontaneously broken symmetry and the existence of massless modes is known as Goldstone's theorem, and the resulting massless modes are called number Goldstone bosons. Great. So I'll just set up on my end and we'll proceed. Okay, great. So now we want to discuss Goldstone's theorem in the quantum theory, in quantum field theory. So generically, the idea is that we have a vacuum state that is not annihilated by some charge, right? So there's a symmetry associated to that symmetry, there's a current, and associated to the current, there's a charge. Sorry about this. I don't know why, but the focus just, yeah. I'll just increase the thickness of my pen and hope that that helps. Okay, so recall that what this is, Q, it's the integral over space of the zeroth component of the current, right? And what does it mean for this to be a symmetry? So if I have some field operators phi I, then the commutator is given by the action of some element of the symmetry group, right? I'll call that G. Right, so Q rotates the fields amongst themselves, right? And the integral, and Q is basically the integral of the zero component of the current. Okay, so these are the two effects you want to keep in mind. So now, what we want to look at is the following, right? So if the vacuum is symmetric, this would be zero, right? Because phi has, let's just take phi to be the field operator, then really it's just going to be the vacuum expectation value of phi, and that's going to be zero. However, when this symmetry is spontaneously broken, this isn't zero, right? And this, again, from the definition we have, so I'll put this at the origin. Without loss of generality, I can do that. Sorry about that. Go back. So I hope you caught that. I just want to put phi at the origin, right? That's my next task. This is a commutator. This is non-zero. Right, so we follow everything that's happened so far. Cool. Now, what I want to do is further take the Fourier transform. So I have the integral over space, which I'll just write as integral sub x for the time being. A0 of x so this is minus y. Although y here is just the origin, so I'll call this y for the time being. Right.
Here, so the field phi, you just switch it up to the origin, right?
Yeah.
So for
Yeah.
that,
So sorry.
So for that, huh?
Yeah. Go on. Sorry.
Yeah. So for that, don't you have to also like include an exponential, which would be like the translation operator, or rather, like why can we live without just like ignoring the translation operator?
Which translation operator are you referring
Like
to?
from like in general, from phi of x to phi of 0, like you can phi of 0 can go to phi of x via a translation operator, right?
Aha. See. Yeah. Okay.
So like why can we get away without including that in this integral?
Well, I mean, I'm not putting phi to. I'm not translating phi. I just want to leave it where it is.
Okay.
So okay. So really, let's just say that this quantity is some function of x, right? So I'll just call this. We'll just call this some function of x, right? And then this is the x integral, right? So what I want to do is take the Fourier transform of this, right, to some function of k, right? Which means that I just have the integral over k of e power I k dot x, right? And then there's an integral of x outside, right? The point is that that quantity is non-zero just because we've not done anything. We've just done the Fourier transform. But notice that if I just, okay, so this f of k, really I should call it f0 of k because it's the zero component of something I would call f mu of k, which is defined as the commutator with the full current, right? So let me write it in momentum space. And the only reason I'm doing this in momentum space is that certain facts are easier to see there, right? And the zeroth component is f0 of k, right? Now, furthermore, I know that this has to be 0. K mu f has to be 0 because of the conservation of the 4 current J mu. Right, so in momentum space, the conservation equation is just given by contracting with K, right? Because contracting with K is equivalent to taking the divergence when I undo the Fourier transform. And now, if you specialize to the setting we have where phi is at the origin and we really have just f naught, right? So if you see f mu is really a function of k0 and some 3 vector k, but this is really some function f mu in our situation, right? We are here of k0 and 0, right? So what we're going to get from this is a condition that looks like k naught, right, of f naught equals 0. K naught times f naught equals 0. Right? That's the only thing that remains of the conservation equations. for the configuration that I've considered here, right? But phi at 0, right? If this has to be true and this has to be true, just give it a second, it'll come back. Right, for both of these conditions to be true, what has to happen? F naught is not 0. If it was 0, then I could conceivably see that its integral is 0. Right? But k naught times f naught is 0. Right? Or rather, the integral of k naught times f naught is also going to be 0. So how do I have both of these things happen?
They kind of cancel each other out.
No, I mean, what cancels who? I mean, there's just two different quantities, right? Here I have just the integral of f naught, and here I have k naught f naught. So how could this happen? I mean, it's a bit of a trick question. If you're not familiar with manipulating distributions, it might not come obviously to you, but remember that the integral of the delta function is generically not 0, but this is 0. 1 second. Don't know, will it come back into focus or not? Yeah, here we are. So what is the derivative of the delta function when I write it in momentum space? Well, it's just going to be k0, right? Which means that the quantity f0 of k has within it delta of k naught. So this f looks a lot like delta, so it doesn't look like I'm making any non-trivial statement there. And then, right, what you can show is if you plug this back into, the definitions that we have and insert a complete set of states, you'll find that phi has to excite. So basically, phi has to excite a massless mode, right? Excites. We'll come back and work towards this conclusion because, you need a little bit of time to see how that works. Right, so that's a mode for which k0 goes to 0 as the 3 vector k goes to 0. Right, that's the meaning of having a linear dispersion relation. So here in a relativistic theory, if you have a linear dispersion relation, then the following statement holds true. Right? Because the relationship between E and P, energy and momentum, is linear for a massless particle. So that's basically the statement of Goldstone's theorem. All we started with was a spontaneously broken vacuum. And you further conclude that there must be a massless mode in it, right? So to see how that works exactly, examine the structure, right? So if you really broke it down, we have f of k naught, right? Which equals, yeah, I mean, it's some, I'll call it g of k naught times delta of k naught, right? It will come back. Right, and this is really the definition of comma phi of 0. Well, this could even be a function of k mu. So really, I don't really care about that. But now this is the part that gets tricky. We need to insert a complete set of states and try and
Yeah,
figure out.
I had a question. So why is like this of the form of delta k naught again? Because
Right. So basically, it came from noting that f has to have a non-zero integral against k naught,
okay,
but that k naught f naught integrated against k naught
okay,
is going
so
to be 0.
right, so that's the okay. This is the only way that would be satisfied. That
Exactly.
okay, got it.
Exactly.
Yeah, okay.
Right. And then now the non-trivial exercise, or I mean, might be trivial if you're used to these arguments, is to figure out why that implies that there's a massless mode in the spectrum.
Right, right.
So okay, I mean, there's an I I've been missing everywhere. So really, this should come with a minus I.
Got it.
And when we insert a complete set of states, this minus I helps, right? Because if I took minus I times the vacuum, J0 of K naught, phi 0, then really I would have something like this. So minus I of that plus I times, the reverse. So I have, this is just the definition of the commutator.
Yeah.
So then I have K, J naught, 0, which is going to be something like,
I think you gotta move here.
Oh, I have to move it up. Thank you. So it's really going to be the norm of this, basically. K times K.
So
Right.
I.
So well, I have an index for I that for phi that I've been missing everywhere. Now, here's what we need to do next is recall that, well, okay, so we could have done this slightly differently, actually. We don't even have to go through all of that. We could have just noted that J acting on phi is proportional to phi, right? Because it's Tij phi j.
Yeah.
Right?
Yeah.
And then what we would have found is that okay, sorry for this confusion. It's not entirely necessary. This is a much easier way to do it. So this is going to be Tij 0 of phi j 0 being on 0. Yeah. And then what I could do is, okay, well, I have to be a bit more careful. It's really the integral over k that gives me this. Right. So it's really the integral of dk0 times all of that is Tij, because there's still the k dependence. Right. So there's two things you can conclude. One, this is non-zero means that phi has a vev, but also the fact that you're going to see the delta of k naught structure here, right, means that you're going to have phi has to, in its mode expansion, contain a massless mode.
Right.
And there is one more way to see this involving the 2-point function. And that's what I'm blanking on right now, because what you should be able to do is also argue that the 2-point function between the phis has algebraic decay in position space, which is the easiest way to see that there's going to be a massless mode. So there's a couple of arguments left there. But at the end of the day, you realize that all you needed to do was argue this fact, and you're guaranteed that there has to be a massless mode in the spectrum. Right. So a mode, so here we're already in the situation where vector k is 0, right? And so You basically have some mode for which k naught goes to 0 as k goes to 0. Right? That's excited by phi. And also, you're going to have a non-trivial vacuum expectation value for phi. Right? This is not going to be 0. And that we'll make contact with in the classical version of this whole story. Because as you always hear, you say that, oh, well, if you have symmetry breaking, then your field will have a non-zero VEV, right? And what does that mean? Well, this is something you not just see in field theory, but even if you did statistical mechanics, right? If you had a lattice system and you have just Z2 symmetry that breaks, then basically it means that the expectation value of the poly sigma Z operator, right? Basically the spin operator is going to be non-zero, right? That means that on average, there are going to be more upspins than downspins. Right? If you had Z2 symmetry, then on average, you're going to have zero expectation value for the sigma Z operator because there's going to be as many upspins as downspins. Right? So this is a signature, having a non-zero vacuum expectation value is a signature of being in the symmetry broken phase. It's a bit more tricky to see what the number Goldstone modes are in the lattice case because they're basically very long wavelength excitations. But the important thing is that these long wavelength excitations have algebraically decaying correlations. Whereas, I mean, the distinction with the massive, so you could ask here, what if I had a massive mode? Then I would have exponentially decaying correlations instead of just algebraically. Right, so that's the signature essentially. So then we can move on to our classical field theory, right? So we'll start with the U1 scalar field. I mean, have there been any questions up until this point? Because this is really the message, and the rest is just going to be realizing this a few more times.
I think it's been pretty straightforward until now. Yeah, except for that part, but no, that was clarified. Yeah. You're on mute, by the way. That's it. Yeah.
So let's go to let's look at a charged scalar field theory. Oh. We'll look at it when it allows us. It's going to take about a few more seconds. I don't know. Okay, it's back. So what is the Lagrangian going to be? It's going to have this structure. Give it an index.
It's not focusing clearly.
Yeah. Right, so that's the Lagrangian. So this is the famous Mexican hat potential. So if you pay attention, it's going to have both a quadratic term and a quartic term, plus some irrelevant constant, right? We don't care about that constant, like lambda v squared, whatever. But notice something about its mass. Something's wrong with this Lagrangian. Right, so let's expand this. So this is just your usual lambda phi 4 interaction, fine. Right. But you'll have lambda over 12.
The potential couples to the field. Is that the problem?
That's the wrong sign.
Exactly. So the mass squared comes with the wrong sign.
But also, what's that to the left of d mu phi star?
Oh, that's the metric eta mu. I'll
Oh,
write it better. It's the inverse metric. Yeah. So the weird thing about this potential is if you wanted to interpret it as a mass plus lambda phi 4, you're going to run into trouble because the mass term, the mass squared term comes with the wrong sign. But you see, we'll see how it's not going to be that much of an issue, really. Okay, so very roughly speaking, the shape of this potential is like this. Well, it's a Mexican hat, which I'm drawing poorly. I'll try to reposition that. But really, you have to imagine that this is being rotated, so that you have 2 dimensions of this. So there's really going to be a circle here. Clearly, the 0 value of the field, right? So this is v and this is phi. The 0 value of the field is not the minimum. And that's actually related to the fact that this mass squared has the wrong sign. Right? But you see, this shape is symmetric under rotating along the circle.
Just a second. Like, isn't the field, like, isn't the mass or like the 0 point like dependent on the field itself? I mean potential itself. Uh,
Yeah, so that's why I'm trying to draw out the potential.
okay, so
Right.
it
So this is
actually
a
depends
known.
on your. It depends on your external potential.
Well, this isn't external, right? It's in the Lagrangian. It's something that I
Okay.
know. Well,
Okay.
how deep this is and so on depends on this number v, but we'll figure out exactly what that is later. The point is that I can rotate this Mexican hat about the axis and it'll stay the same, provided I'm sitting over here. So but the issue is that this isn't really the true minimum of the function. Right? The minima lie along this circle, which means that there's a degeneracy of minima, right? A degeneracy of vacua. But they are not corresponding to the 0 value of the field. We'll find that their value, like the value of the field over here, is actually a non-zero vacuum expectation value related to V. Also, moving along here, you would expect to sort of vary the field along this circle. You would expect to cost no energy, right? Because of the shape of this potential. Which is really the effect of having this one Mambo Goldstone mode that we'll discover. Because I could have, if I have a, so there's a reason why massless fields are analogous with, well, they are gapless excitations. If I thought of this as coming from some long wavelength description, this field theory is coming from some long wavelength description of some quantum system on a lattice, then these would appear to be gapless excitations, right? So I can only have arbitrarily low energy massless excitations. I can't have arbitrarily low energy massive excitations unless I make the mass arbitrarily low, right? So here's your Goldstone theorem in action. But first we have to ask, okay, how do I get there, right? So what do we expect to do to move forward? We'll have to. So we've realized just from looking at this picture that expanding this field around the zero value is the wrong thing to do. Right? So let's first look at the structure of the potential and figure out what is its minimum. Right? So you have lambda over 4 factorial phi star phi minus v squared whole square. Right? I want to find where its minimum is. This is going to be a silly exercise because you can almost see it, but let's do it anyway. It's going to be another delta phi here. Okay. So it's going to be well, I'm just going to reorganize this so that the structure becomes clear. So I think there's a minus sign somewhere that I'm getting wrong. Ah, yes, here. This comes with a minus sign. Which means phi star phi has to equal v squared. There's a reason I grouped it as delta of phi star phi, because you come to the same conclusion by reducing it down to delta phi, but it just makes the very obvious statement that the minimum of this potential is at its zero value when phi star phi equals v squared. Right? So if you thought of phi as having some, it's some complex number in field space, right? So it roughly has this structure, right? So it has a phase and it has a magnitude. The vacuum corresponds to when h squared is v squared. This is just the same as saying that this is mod phi squared. So the radius of that circle that I drew before is v. Right? Okay, I mean, another thing that we should have noted was that this theory has a U1 symmetry. And that's very easy to realize just from the fact that you only really see the combination of phi star phi, right? You don't actually see phi squared, any function of only phi or only phi star, right? So in the combination phi star phi, if I include a phase, it'll cancel. So that's the U1 symmetry. Cool. Now, what we have to do is expand the field around the minimum of right? So this is like the minimum value of the field, right? When something like v e power I pi 0. Right? So pi 0 is some constant, right? So now what I want to say, I wonder what name I should call this. I'll call it little delta phi. right? So the little delta phi is basically fluctuation around the vacuum. And for the purposes of understanding just the spectrum of the theory, little delta phi is treated as though it were infinitesimal. You don't have to, but let's see what happens if we do that, right? What is the structure of this? It is delta H plus V e bar I pi naught plus delta pi. So before we proceed with plugging this back into the action and going through some of the motions, can any of you guess which one will be the massless Goldstone mode here? I mean, think about the circle in the Mexican hat.
Like what we found previously, right? The phi star equals.
No, I mean, what's going to be the massless mode? It's going to be pi.
Oh,
This delta pi.
yeah.
Because that's the one that goes around in the circle, right?
Right.
So let's see how that all works out. So,
So it's just something like saying there is a ground massless state, and then these are the massless excitations that are created.
well, it's really like understanding what happens to the theory when you so the real physical, there's a fluctuating field here is delta phi. So what's the theory for delta phi? What's the Lagrangian for delta phi? That's what we want to find.
Okay.
And from that Lagrangian, we can discover what are the mass terms, etc. What are the interactions? How can we discover what the mass terms are? We just look at what's quadratic in delta phi. I feel like that's as far as we're going to get today, but let's see. We have delta H plus V. Well, let me just do this differently. Right. So the vacuum, both V and pi 0 are constant, so there's going to be no derivatives, right? So the derivatives are all going to only hit this delta phi, right? To be d mu delta phi star. Right. So that's going to be this is a bit shabby, but well, H is a real number. So these phases will cancel. They'll just give me 1. And then I'm going to have well, actually, there's an I here, which makes this a plus. Right, not to forget that this is I delta phi. So again, great. So that's the kinetic term. Now the potential is a little bit more interesting, right? So the potential has the structure of phi star phi minus v squared whole squared. Now, before we go any further, will I see a quadratic term for delta H. Yeah, we will though, because you see, phi star phi is going to be, is just delta H squared. The pi stuff all cancels, right? I have e power I pi naught plus delta pi, and then e power minus I pi naught minus I delta phi, or delta pi. So those will just cancel. This is just delta H squared. Which means that when I expand this, I'm going to get something like 4 factorial of delta H to the fourth power, which we'll neglect really because we want to take small fluctuations. Sorry about that. This is the wrong equality. Right, so I have delta H to the fourth power But you see, there's a term quadratic in delta H squared, but no term quadratic in delta pi. So delta pi is massless. Delta H is massive. And the mass is set by the coupling and v squared. Still. Right. So what have we really learned? We've learned that here, the massless field, right, that parameterizes this direction in field space is pi. And that's exactly what we expected. Right? Whereas anything that parameterizes this direction is h. So you see that you have a vacuum that breaks the U1 symmetry. Because if I put, so imagine I have this Mexican hat, sombrero, and then I put a dot somewhere on the ridge of the hat. Well, clearly I know that there's a difference if I move the dot, right? Like that's not symmetric. If I put a dot right on the top and I rotate it, then it's going to be symmetric, right? So the ground state, the vacuum state, is the one where the dot's at the bottom, right? And that breaks the symmetry, right? But instead of having the symmetry generator that rotates around this vacuum, I have a massless field. And you see, this massless field has the weird property of almost being like the parameter of some gauge transformation. And that's exactly what's at the heart of the abelian Higgs mechanism. Because you see, I can shift pi by a constant. It's a phase. And I'll, phi only has a kinetic term, right? If I just have some term like this, I can shift pi by a constant and nothing will happen. So there's a shift symmetry, right? And this is just enough to absorb the gauge transformations of a massive vector field. Right? I have some term like a squared, right? Then I'm going to have shifts by something like delta of some scalar field squared. Right? The gauge parameter is acting as though it was a scalar field. Right? And so these two will cancel against each other, their transformations. And that's called the Stickelberg mechanism. And in some sense, it's like saying, if I add a compensating scalar, I can reinstate a gauge invariance that was actually lost, right? But this compensating scalar will have potential of its own, then really you have a Higgs field. So that's what we'll get to next time. The statement there is that the gauge field is eating up the Nambo-Goldstone mode. And that's providing the extra degree of freedom. Like, note that if I have a massless gauge field, a massless gauge field in 4 dimensions, then there's 2 degrees of freedom that it propagates. right? Like take U1, you really have 2 degrees of freedom, 2 polarization modes. But if you have a massive gauge field, it propagates 3 degrees of freedom. So where's that extra degree of freedom coming from? It's coming from the Goldstone mode. So that's basically the mechanism at the heart of the Higgs mechanism. That process at the heart of the Higgs mechanism, which we'll get to next time.
Yeah, I guess once I see it, it'll become clear. Right now, it's
Yeah.
a bit hazy. Yeah, how it acts like
So,
a gauge field. Yeah. Yeah.
so are there any questions? For now, I guess I'll close this down and also leave the meeting.
Yeah, I think. Yeah, those were all the questions I had. The next time, I feel like it'll get clarified. Yeah.
Okay, how about everybody else? What do you all think?
I mean, this was good. Like, I still need to understand like how exactly like there is this sort of like coupling of V with the field itself, right? So
Yeah,
there's
but
so that
right. I mean,
relation is
V is
something.
just a constant, right? It doesn't really like
Yeah.
you could say. Well, I mean,
Hmm.
if I have a coupling constant, it sits in front of the term in the Lagrangian. It's kind of coupled anyway,
Mm-hmm.
right? So it's the same thing. It's just a
Mm-hmm.
weird way of writing it. I mean, because the alternative is to write it as though you have a wrong sign for the mass term, or like
Mm-hmm.
mass squared. It's as though you had an imaginary mass,
Yeah.
which is strange. So instead, you write that potential.
Thing,
So,
so,
mhm.
the thing I find kind of like weird about the entire Higgs mechanism in general is like, even though there's so much like actual like physics going on, like the actual calculation is you do is basically some really simple algebra. And sometimes like it's kind of hard to wrap your head around the fact that like such simple algebra can give you like you know, so much out of it.
Yeah, no, for sure. I mean, the other thing to note is that constantly you switch in this story between what's classical and what's quantum.
Yeah.
So you need to kind of bear in mind there is some quantum version of the whole story that's being played out, and yeah, that's why I went through the goals first in quantum field theory, so that we can see what's going on.
Yeah. Okay, I guess I'll stop the recording now.